Randomized distributed algorithm. Introduction. This lecture focuses on specific type of distributed algorithm which employ randomization. Randomization has proved to be a very powerful tool for designing distributed algorithms as far as many other areas also. It often simplifies algorithms and more importantly allows us to solve the problems in situations where they cannot be solved by the deterministic algorithms or with a fewer resources than the best deterministic algorithm ever solves. So, in this particular discussion or lecture, we will see the power of randomization if basically is used with the, the distributed algorithm, then it is going to solve some of the impossibility results also, but how they are going to be solved with the same problem statement or with a modified problem statement, that we are going to see. So, randomization, if it is merged with or it is given as information to the distributed algorithm, then we are going to see the intricacies in this part of the lecture. So, this lecture extends the formal model to include the randomization and describes the randomized algorithm for leader election problem. So, leader election problem will be a case study where we will use the randomized approach or randomization, and we will basically discuss the randomized algorithm for leader election problem. Randomization allows us to overcome impossibility results and lower bounds by relaxing the termination conditions or the individual liveness properties. Distributed mutual exclusion algorithm, a case study. Now, the problem definition, we will basically see that the same problem definition which is impossible, now we will take up its weakening the problem definition, and let us see that how using randomization we are going to solve it. So, a randomized algorithm is an algorithm that has access to some source of random information, such as that provided by flipping a coin or rolling a dice. So, more formally, extend the transition function of a processor to take as an additional input a random number drawn from a bounded range under some fixed distribution. So, what is important here is that the addition of random information alone typically will not affect the existence of impossibility or the worst case bounds. So, for instance, even if the processor have access to the random numbers, they will not be able to elect the leader in an anonymous ring or solve the consensus problem fewer than f+1 rounds in all admissible executions. So, randomization with weakening of the problem statement becomes a powerful tool to overcome these limitations, which are basically proved using the impossibility results and also the lower bounds. So, usually weakening involves the termination condition. For instance, a leader election must be elected with a certain probability. This becomes a weakening of the problem statement. So, a leader must be elected with a certain probability. So, this becomes a problem statement or a new problem statement, and this we will see how using randomization we are going to solve. So, randomization and weakening of the problem statement together will solve the purpose or will solve the impossibilities and the bounds which are being proven. Now, this randomization differs from the average case analysis of the deterministic algorithm. In average case analysis, there are several choices as to what is being averaged over. One natural choice is the inputs. So, there are two difficulties with this averaging issue. First is determining an accurate probability distribution on input is often not practical. Another drawback is even if such distributions can be chosen with some degree of confidence, very little guarantee about the behavior of the algorithm on a particular input. For instance, even if the average running time over all the input is determined to be small, there still could be some input for which the running time is enormous. In the randomized approach, more stringent guarantees can be made. Because the random numbers introduce another dimension of variability even for the same inputs, there are many different executions for the same input. A good randomized algorithm will guarantee a good performance with some probability for each individual input. Typically, the performance of the randomized algorithms defined to be the worst case probability over all inputs. Now, randomized leader election problem. The simplest use of randomization is to create an initial asymmetry in the situations that are inherently symmetric. For example, if we say an anonymous ring, so anonymous ring where the IDs are not uniquely assigned, so they becomes anonymous rings where the IDs are not distinct. Now, we have seen the impossibility result that there is no non-uniform anonymous algorithm for a leader election in a synchronous ring. So, that impossibility result reminds that if let us say that the nodes are not or having the distinct IDs, then basically this will create the problem of the symmetry, and in that symmetry the state machines of all the processes will be the same in every execution, hence the leader will not be elected in that case, in spite of the non-uniform. In spite of non-uniform, that means in spite of knowing how many nodes are there in the ring. So, the simplest use of randomization is to create the initial asymmetry in the situations that are inherently symmetric. That example we have seen. So, one such situation is anonymous ring, where the processors do not have distinct IDs. So, it is impossible to elect a leader in this particular problem setting. So, it is said that it is impossible to elect the leader in this problem setting. Now, from the earlier theorems, we have also seen that there is no non-uniform anonymous leader election algorithm in a synchronous ring. This particular impossibility result also holds for the randomized algorithms. However, the randomized algorithm with the modified formulation of a leader election, that is, the leader is elected with some probability, with this weakening of the problem statement. Now, let us see that whether this particular weakening of the problem statement, and if we add the randomization, whether it is going to solve this particular impossibility result and give up with the randomized leader election problem. So, a variant of leader election problem that relaxes that condition that eventually a leader must be elected in every admissible execution. So, relaxed version of a leader election problem requires two properties to be satisfied. The first is called safety property. Safety property says that in every configuration of every admissible execution, at most one processor is in the elected state, meaning to say that in no situation or in no admissible execution there can be more than one leader elected in an algorithm, then it will become the wrong or it will violate the safety conditions. So, safety conditions ensures that in every execution or every admissible execution the algorithm produces at most one leader. The other condition is called the liveness condition. So liveness condition says that at least one processor is elected with some non-zero probability. Here we have included the weakening of the problem statement. In that weakening is affected in the liveness condition. So liveness says that at least one processor is elected with non-zero probability the leader. So leader is now the modified liveness condition says the leader is elected with some probability. So safety property has to hold with certainty, as I explained. That is, the algorithm should never elect two leaders or more than one leaders. And this is the safety property. So there is no weakening in the safety property. Safety property has to hold with the certainty, as we have seen earlier. The second property called liveness property. Liveness condition is relaxed, and the algorithm need not always terminate with a leader. Rather, it is required to do so with the non-zero probability. So an algorithm that satisfies this weakened liveness condition can fail to elect leader either by not terminating at all or by terminating without electing a leader. So we are going to take up this particular issue, and we will see an algorithm designed with this weakening the liveness condition to elect a leader using the randomized approach. And we will see also the remedy, that if the leader is not at all elected at the termination of the algorithm, how are we going to basically resolve this. So the first algorithm which we are going to discuss is the synchronous one-shot algorithm, and this is the randomized algorithm. So let us first consider the synchronous ring. So in that synchronous ring there is only one admissible execution on this anonymous ring for the deterministic algorithm. Now for a randomized algorithm, however, there can be many different executions depending on the random choices. So as you know that in anonymous ring, for a deterministic algorithm there is only one admissible execution, and where all the states are the same, the state transitions are the same, hence there is no asymmetry, hence the leader cannot be elected. But for randomized algorithms, here there are many different executions. Why? Because that depending on the random choices of the IDs. So asymmetry can be introduced with some probability in the randomized algorithm. So the approach that is used to devise the randomized leader election is to use the randomization to create asymmetry by having processors choose a random pseudo identifiers drawn from some range and then execute a deterministic leader election problem. So in this problem setting, we will see that range of values is from 1 and 2. That means the pseudo random pseudo identifiers are from the set of only two numbers 1 and 2, and then execute the deterministic leader election. And let us see that if this particular choosing the number out of these two range of numbers 1 and 2, whether the deterministic leader election problem can tap this asymmetry and elect a leader, or it is failed to elect a leader because of the symmetry. So a deterministic leader election with these properties is the following. So each processor sends a message around the ring to collect all the pseudo identifiers. Let us assume this leader election, this particular ring. So here every processor will send its ID, which is drawn out of a random range of numbers. Here we are considering only 1 and 2. So this particular process will toss a coin to select one of these two numbers, or randomly pick one of them out of these range of numbers given, and that will become its ID, and this ID will be sent on the left part of the edge. The next process connected by an edge will receive this from the right side of the ring. So when the message, so basically it will collect, so this particular message will collect the C2 identifiers, or it will add its own ID, and that will circulate around the ring. So after n rounds, if n number of processes are there, so n rounds, then all the processors will know the IDs which is being selected here by the processors, and the one which is having the highest ID will be elected as the leader. So when the message returns after collecting n C2 identifiers, the processor knows whether it is unique maximum or not. Now coming the algorithm, with that idea, the algorithm goes like this. In this algorithm, the C2 identifier is chosen to be 2 with the probability 1 by n, and the number 1 is chosen with the probability 1 minus 1 by n. So the range of numbers is only 2 numbers, so IDs will be chosen by n different processors. So the probability of choosing 2, let us say, is 1 by n, is the probability of choosing number 2. Similarly, the probability of choosing number 1 will become 1 minus 1 upon n. So n is basically the number of processors in the ring. So this becomes the first step of the algorithm. Thus each processor makes use of its source of randomness exactly once, and the random numbers are drawn from this range that I explained. The set of all possible admissible executions of this algorithm for the fixed ring of size n will contain exactly one execution for each element of this set, which will basically be nothing but a vector, which vector of size n, which will be containing the elements either 1 or 2, and that is represented by a big R set. That is, by specifying which random number 1 or 2 is obtained by each of the n processor in its first step, we have completely determined the execution. So given an element R of R, then the corresponding execution will be denoted by execution of R. So that means in a particular execution, we can admissible execution, we can denote it by XR of that particular instance, which will. So the algorithm, which is called leader election algorithm, using randomization in an anonymous ring for a particular process Pi, and this particular algorithm will be implementing or will be running on all processors, that is ranging from 1 to n minus 1. So if there are n processors, so this algorithm will run on each node of the topology, which is organized in the form of a ring. So initially, spontaneously or upon receiving the first message, the IDs will be picked. That means a processor will pick an ID 1 with a probability 1 minus 1 by n, and ID 2 with a probability 1 by n. So it will pick a number 2 with a probability 1 by n. So then after picking one of these numbers randomly, then it will send this number as an ID of a particular process to the left of the ring. To the left means this ID will be sent. ID of I will be sent to the left. Upon receiving this particular message S from the right, this particular process will check if the size of this S is equal to n. That means this particular message is already flown n different times in the ring, and n are the number of processes. That means it has collected all IDs of n different processes. So if it is n, then the ID, if ID I is the unique maximum of S, then it will be elected. That node will be elected, else the node becomes non-elected. So if that particular ID is not maximum of all the other n's, then the node will be non-elected. If it is not circulated n times, then it will send this particular ID affixing its ID. So it will contain ID I and ID j, and this message will be sent to the left, and so on. So this way this particular size will grow. When it will reach over here, it will contain all the n IDs listed in that particular message, and by that it will check whether its ID is maximum among all the unique maximum, not only maximum, but it should be a unique maximum. So that means if, let us say, two nodes are picking ID as 2, so there cannot be two leader elected. So obviously there will not be any leader elected. So the leader will be elected only in one case, when one node will have the ID 2 and all other node have the ID 1. So this is only one case when the leader is elected. So definition, let P be the predicate on executions. For example, at least one leader is elected, then the probability P of that event is nothing but an execution that satisfies that particular predicate. Analysis, what is the probability that the algorithm terminates with a leader? So this happens when a single processor has the maximum ID 2, and that means only one processor has the maximum ID 2 and all other processors are having the ID as 1, then only the leader will be elected. The probability that a single processor draws 2 is the probability that n minus 1 processor draw 1, and one processor draws 2 times the number of possible choices of the processor drawing 2, that is. That means only one processor draws 2, that probability is 1 by n, and all other processors, n minus 1 processors, are drawing 1, that probability is 1 minus n, and n minus 1 processors will draw. And this kind of how many times is possible choices of processor drawing 2 is basically n C1. So if you simplify, then this particular part of this particular formula will cancel n by n, so it becomes 1 minus 1 by n minus 1. This is the probability that the algorithm terminates with a particular leader. Now we will see that what is the probability that all n. So what is the probability if we take the difference? So we will see that this is having a higher probability than this particular probability where none of them has chosen 2. So that means this particular probability of termination is converging if the number of nodes is basically going to be a large value. So it will converge to a value which is 1 upon e. So this is a constant. So the probability that the algorithm terminates is a constant, and that is 1 by e, and that is shown in the next slide. So the same thing is 1 by E, that is the probability of choosing of that algorithm terminates with a leader is 1 upon E. Now it is simple to show that every processor terminates after sending exactly n messages. Moreover, at most one processor terminates in an elected state. In some executions, for example, when two processors choose C2 ID 2 of 2, then no processor terminates as a leader. Why? Because safety condition says that only there can be only one leader, then only the algorithm terminates successfully. However, the above analysis shows that this happens with a probability less than 1 minus 1 upon E. The message complexity. So the theorem for this analysis or this algorithm says that there is a randomized algorithm that with the probability C, which is greater than 1 upon E, elects a leader in a synchronous ring, and the algorithm sends how many messages? Order n square messages, because we have taken the n square algorithm and deterministic algorithm and converted into a randomized algorithm with relaxed live condition. Now we have seen that this particular algorithm which we have just seen may not terminate with a leader elected and may end without any leader elected, because if there are two nodes with a maximum value, two or more nodes with a maximum value, then leader will not be elected. So leader will only be elected in a condition when only one node is having the maximum value and all other nodes are having the other value, elected as non-leader. So we are now going to see the next step forward. That means we want that algorithm should be terminated after several iterations. That means this algorithm is to be now iterated over more than one times or more than one round, finally when it elects a leader. So the synchronous iterated algorithm and the expectations. So we are now going to discuss the modification of the previous algorithm, or how the previous algorithm is to be iterated over the rounds so that it can elect a leader and terminate after that. So then we will be calculating its expectations. So it is pleasing to know that the probability of termination in the previous algorithm does not decrease with the ring size. So as we increase the ring size, the probability is not going to decrease. So hence it's basically a scalable, or it's a good news. However, we may wish to increase the probability of termination at the expense of more time and the messages. The algorithm can be modified so that each processor receiving a message with n C2 identifiers checks whether a unique leader exists or not. That means in the previous algorithm, if we see at 5 to 7, what we can do is, after seeing the IDs which are coming on the message, and if it is found that more than one maximum number, that is 2, is present in the message, then basically that iteration or this algorithm should be terminated, because it is not going to elect the leader. So it is an early detection. That means this particular 5 to 7 lines, during these lines we can insert a condition, and this algorithm will come out of that current iterations, and it will again reassign the C2 IDs to the node and restart again. That is called iterative algorithm. So we are now discussing about that iterative algorithm, because we are interested that algorithm should terminate with a leader. So if not, the processor chooses a new C2 IDs and then iterate the algorithm that I have told you. We will now show that this approach amplifies the probability of success. Let us consider the second option in more detail. In order to repeat the algorithm 1, each processor will need to access the random number source multiple times, in fact potentially infinitely often, saying that the random number C2 random IDs 1 and 2 in the algorithm number 1 is accessed by the nodes exactly 1 times. But now when you are iterating, so this access of this particular number by the same processor maybe a multiple times, because these IDs, if they are going to change, maybe in some admissible execution a leader is going to be elected. So that is why there is a modification that the processors will need to access the random number source multiple times, and in fact potentially infinitely often. To completely specify the execution of the algorithm, we will need to specify for each processor a sequence of random numbers that it obtains. So in this process, every node, after picking up a random number out of this particular range, will generate a sequence of random numbers, and every processor will obtain this kind of sequence. Let R becomes be the set of all n tuples, each element of which is possibly an infinite sequence over 1, 2, that is the range of numbers. Now the analysis of this iterative algorithm. The probability that the algorithm terminates at the end of kth iteration is equal to the probability that the algorithm fails to terminate in the first k minus 1 iterations and succeed in terminating the kth iterations. So that means if the algorithm terminates in kth iteration, means that it is not successful in the previous k minus 1 iteration, and it is successfully terminating with a leader elected in the kth iterations. So the analysis of algorithm 1 shows that the probability of success in a single iteration is 1 upon e. So because the probability of success or a failure in each iteration is independent, the desired probability of terminating at kth iteration is given by this particular formula. 1 minus c is basically the probability that it is not successful in terminating with a leader elected. So 1 minus c, and this will repeat for k minus 1 times, and then at kth time this is the probability to elect a leader. So this is the total probability that after kth iteration the leader is elected during the iterative algorithm. So this probability tends to 0 as the k tends to infinity. So if the k tends to infinity, this particular probability becomes 0. Thus the probability that the algorithm terminates with the elected leader is 1. So this is the good news, that after sequence of rounds or iteration, the algorithm will elect a leader with a probability 1, or definitely elect a leader. So the time complexity of this iterative or iterated algorithm is like this. Now the worst case number of iterations, if it is infinite, the expected number of iterations, if we see, is 1 upon c, is less than e, or the value of e is 2.7 something, or you can say that the expected number of iterations is 3. That means within 3 iterations some leader will be elected, and that is not a bad number. Let t be the random variable that for a given execution is the value of the complexity measure of interest for that run. For the instance, the number of iterations until the termination. Why we are doing is because the worst case number of iterations is infinite. That particular value is meaningless to us. So in this particular iterated algorithm, randomized algorithm, we will take the expected value of the total number of iterations, and then the message complexity will be discussed or will be considered in that terms of average, not in the worst case. So ET be the expected value of t, and t is the random variable for a given execution, is that the value of the complexity measure of interest for that run. So that is the number of iterations until the termination. So this particular expression will lead to this particular theorem that there is a randomized algorithm that elects a leader in a synchronous ring with a probability 1 in 1 upon c times n, that is E times n. So within E times n number of expected rounds, the algorithm terminates with a leader, and this particular algorithm will send order n square messages, expected messages in each round. So the conclusion, randomization has proved to be a very powerful tool for designing the distributed algorithm, and in this part of the lecture we have taken a case study of the leader election problem in an anonymous ring, and we have seen that by doing the weakening of the problem definition, that basically leader is to be elected with certain probability, that randomization is able to solve the problem of leader election in anonymous ring. It allows us to solve problem in the situation where they cannot be solved by the deterministic algorithms. This lecture extends the formal model to include the randomization and describes the randomized algorithm for leader election problem. We have presented two randomized algorithms, synchronous one-shot algorithm with order n square messages and synchronous iterated algorithm with the order n square expected messages. Thank you.